Hello everyone, my name is Bekasıl Aygaраев. I am math teacher at NIS School of Chemistry and Biology at Kızılorda. And today we are going to learn about areas bounded by a curve and the x-axis. In simple case, y is equal to ax to the power of n. So let's get started with a warm-up. Here we have to find the area of this non-standard shape. Well, for this irregular shape we don't have a formula, so we cannot find it straight away. But if we complete this into a rectangle where we can find the area by multiplying, say, lengths and the width, we can find its area. So here is the solution. Here we have these yellow parts and we have this pink colored part and we have to find its area. So it will be the area of the big rectangle subtracted by the yellow ones, the one that we don't need. So the area of the big rectangle will be 3 plus 4, which is 7, and then we have 2 plus 12, which is 14. So the area will be 14 multiplied by 7. And we have to subtract the yellow ones, and that will be 2 multiplied by 3, and then plus we have another rectangle. Oh, it's more like a square. And here we have to multiply 4 by 4. So that will give us 76. That is the area of my pink colored irregular shape. So when we don't know the correct formula for a non-standard irregular shape, we can find the area by completing it into a rectangle or any other geometric figure. So here's a question: how can we find an area of an irregular shape like this, where we have a curve and it has its own function, and the area below it between the x-axis and our curve? How can we find it? Well, here are some ways, and today's topic, as you might have presumed, it's about integration and trapezium rule. We will find today, using integration, the areas bounded by a curve and the x-axis. So lesson objectives. We have 2 lesson objectives today. 1137, know the definition of curvilinear trapezoid. And the second one, 1139, apply formula of Newton-Leibniz to find the area of curvilinear trapezoid and calculation of their definite integral in the simple case function of the form y ax to the power of n. And here are our success criteria. As our lesson will come to an end, we have to learn about integration process. We should be able to understand it, know the definition of trapezium rule, and be able to estimate the area of curvilinear trapezoid, and be able to calculate definite integral, understand and evaluate definite integral when we are given that it gives an area. Also, we need to understand the application of integrals. Here are some terminology that might come in handy. They are in 3 languages: English, Kazakh and Russian. Let me read them. Antiderivative, алғашқы функция, первообразная. Indefinite integral, анықталмаған интеграл, неопределенный интеграл. Definite integral, анықталған интеграл, определенный интеграл. Curvilinear trapezoid, қисық сызықты трапеция, криволинейная трапеция. Constant, тұрақты, постоянная. Bounded area, шектелген аудан, ограниченная площадь. Application of integral, интегралдың қолданысы. Применение интеграла. Let's start from trapezium rule. Well, here is the definition of trapezium rule. It's a way of estimating the area under a curve. So I have highlighted the word estimating, which means that we're going to estimate the area. We're not going to find a precise answer, exact answer, because trapezium rule cannot give you the correct answer. It will give you a rough estimation. But if you are going to split the area into a lot of intervals, your estimation will get better and better. Well, here this rule works by splitting the area under a curve into a number of trapeziums, which we know the area of. Here in this picture we are given 8 trapeziums. But if we divide, let's say, into 10 or 12 or 20 trapeziums, our estimation will get better. Here our intervals have the same length, h, but the heights are different, and our heights are the functions, and we know how to find them and how to calculate them, because we know the x coordinate of that function. And if you want to find the area under a curve between points x0 and this one, and then xn and this one, we divide this interval into smaller intervals with lengths of h. So each one is h. For example, the first trapezium, it has an area of a1. And how do we calculate it? Well, we know the height of the first function. We just insert x0 into the function, and we find f of x0, and then we find f of x1, it's this function, and then we get the average of these two heights, which is around here, for instance, and when we multiply by h, we get the area of the first trapezium. And we will find the area of the second, third, fourth, fifth, sixth, seventh, and eighth, and then we are going to add them. That will give me the whole area that I want. And the formula in the general form will be like this. Here h is the interval, 1/2 is for average, f of x0 and f of xn. We're going to take the first function, the first height, and the last one. We're going to add them, and then we add and multiply by 2 the summation of all other functions which are in between those two, the first height and the last. And let's solve an example. Use trapezium rule to estimate the area bounded by a curve y is equal to x squared and the x-axis in the interval 0 to 3. Oh, this is my function, it's parabolic, and the function is y is equal to x squared. Here, under this curve, we have 3 trapeziums. I have used 3 intervals, but if I have used more, my estimation would be better. But for easy calculations, I have taken h is equal to 1. So you see, my intervals are 1, 1, and 1. So this is my x-axis, this is my function, and the area between them is going to look like this. First, of course, we have to find the functions, the heights. Let's say f of 0 is equal to 0. Why? Well, if you insert instead of x 0, you'll get y is equal to 0. And this is the point right here. at the origin. F of 1 is equal to 1. As you can see from the graph, when we have 1 here, we get 1. And for f of 2, we have 4. As you can see, 2, that is 4. And for f of 3, we get 9. See, 3, it's 9. And when we put here 3 to the square will be 9. So when we know all those heights, we can put them into our formula and find the area. Here you see it's an estimation. 1 over 2, because we take the averages, multiplied by h, our intervals, multiplied by f of 0 plus f of 3, as you can see, the first and the last height, and plus 2 multiplied by all other heights. Well, we have f of 1 and f of 2 right here. And that will be my h is equal to 1, of course. F of 0 is 0 plus 9 plus 2, and 2 multiplied by 1 plus 4, and that will be 1 over 2 multiplied by 9 plus 10. That gives me 9.5. So that's my answer for the area below the graph. Let's start solve another example. Here it's a little bit more difficult because our function is a square root of x, and here I have used 4 intervals. As you can see from the picture, I have used 4 intervals, which is better than 3 intervals, of course. Here, the first thing that we should do is to find the heights. F of 0, it's going to be 0. If you insert here 0, you get y is equal to 0. And from the graph, you can see that point right here. And f of 1 is equal to 1. That's the point right here, which gives you 1. Of course, if you put here 1, square root of 1 gives you 1. F of 2 is equal to square root of 2. Of course, here it's 2. You put x is equal to 2. You get something that is less than 1.5. That's square root of 2. And if you put 3 instead of x, you get square root of 3. That's pretty much right here, which is more than 1.5 but less than 2. That's square root of 3, of course. But if you put 4 here, it will be square root of 4. That gives you 2. And the point right here 4, and you get exactly 2, of course. So the area will be estimated like this: 1 over 2 multiplied by h, f of 0 plus f of 4, you know, my first function, my first height, and the last function and last height, plus 2 multiplied by all other functions that are in between, f of 1, f of 2, and f of 3, like this. So when we calculate and when we insert the numbers, we get this number. That's my area, 5.146. So here are definite and indefinite integrals. Well, we have learned those, but we might want to recall them, because when we are going to calculate the area bounded by a curve and the x-axis, we're going to need integrals. So if you are given a function f of x, the antiderivative of f of x is a function f of x, well, capital F of x, whose derivative is equal to f of x. This means that capital F of x derivative is going to be f of x. So indefinite integral is this expression where we don't have those limits, upper and lower one, and that's the family of antiderivatives, right? For definite integral, we have this expression where we have these upper and lower limits, and it's a subtraction of two antiderivatives, which gives you a number. And that number is the area under a curve. Here I have highlighted that word. Definite integral gives the area under a curve. This formula is also called Newton-Leibniz formula. And to understand more about this sentence, this statement, the definite integral gives the area under a curve, let's watch a video from William Land website.
The indefinite integral of a function f is an entire family of functions. We call them antiderivatives of f. By contrast, the definite integral of f is a single number. How is the number defined? Let f of x be a function defined in the interval from a to b. Look at its graph. Can the area included between the graph of f and the x-axis be calculated somehow? Let us try to approach it by rectangles. The number f of x1 times c minus a plus f of x2 times b minus c represents the area of the two rectangles if f takes on only positive values in the interval from a to b. We can get a better approximation if we divide the interval from a to b into smaller subintervals and use them as bases for new rectangles. The rectangles cover more and more closely the region between the graph of f and the x-axis. If the sum of the areas of these rectangles, represented by the products f of x, times the length of the subinterval approaches a particular number independently of how the partition is performed, then this number is defined as the definite integral of f in the interval from a to b. Note that when f is negative in some subinterval of the interval from a to b, some rectangles fall under the x-axis, and the product f of x times the length of the subinterval is negative. Therefore, it differs in sign from the area of the corresponding rectangle.
Now let's continue our lesson. To be able to solve our integrals, we have to recall some properties and formulas. For that, here x to the power of n, if we integrate these, we get x to the power of n plus 1 divided by n plus 1 plus integration constant. This is the antiderivative. And a good example here, x to the power of 2, so our n is equal to 2, will be x to the power of 3 divided by 3. Why 3? Because we put here 2, that will be 2 plus 1, that's 3 right here, and then we have 2 plus 1, it will be 3, okay? And when we integrate a function multiplied by a constant number, we can take this constant number out of the integration sign. And example here, 5x, if we integrate, we can take 5 and integrate the rest. The integrals of a sum is the sum of the integrals. So here, if we have different functions, we can integrate each one separately, like this. 2 plus x, if we integrate 2 and we integrate x separately. So these are the properties and formulas that will come in handy when we solve some examples for integrals. Let's start with an easy example. Find the area under a curve y is equal to x, which lies between lines x is equal to 0 and x is equal to 3 and x-axis. So x-axis is this one, okay, x is equal to 0, this one, x is equal to 3, this one, and y is equal to x, it's this one. So the area enclosed by all those lines will be the yellow one. This shaded area will be calculated by an integral. We should integrate from 0 to 3. So you see it's from 0 to this point, which is 3. Okay, our function is x. Y is equal to x. This is my function. And the area under it will be calculated with this formula. Okay. First we have to calculate the antiderivative, which will be x squared divided by 2. The limits will be from 0 to 3, and it will be, first we insert 3 instead of x, and we get 3 squared divided by 2, minus, and we insert 0 instead of x, and we get 0 squared divided by 2, and when we calculate this we get 4.5. That's my answer. Okay, example 4. Find the area enclosed by x-axis. And x is equal to 1, x is equal to 2, y x squared. So this red line is my function, y is equal to x squared. Okay, so the points are 1 and 2. So my integral will be like this. From 1 to 2 we integrate our function, which is x squared. And that will be x cubed divided by 3, my antiderivative, from 1 to 2. So we insert 2 first, and then we insert 1, and we subtract our results. So 2 cubed divided by 3 minus 1 cubed divided by 3, that gives me 8 minus 1 divided by 3, that's 7 divided by 3. That's the area. Okay, example 5. Find the area enclosed by x-axis. X is equal to 1, x is equal to 4, y is equal to square root of x. So remember we used trapezium rule for square root of x to find the area, and our estimation wasn't precise. But now it's going to be much more precise. It will be precise because we are going to use integrals. So my points are, starting point is 1, the ending point is 4, my function is square root of x, and the area between the x-axis and my curve will be calculated by this formula. Area is equal to, from 1 to 4, square root of x multiplied by dx. So in order to calculate this integral, we need to use our formula, which is x to the power of n gives me x to the power of n plus 1 divided by n plus 1 plus integration constant. So this is the antiderivative. So here my integral will look like this. Square root of x will write as the power of x, x to the power of 1 over 2. So it will be, by using this formula, it will be 1 over 2 plus 1 divided by 1 over 2 plus 1 from 1 to 4, of course. So when we put those numbers 4 and 1, we get 14 divided by 3, and that's my answer. Let's go to example 6. Here we have to find the area enclosed by x-axis. This one, okay, x is equal to minus 1, okay, this h, right, this line, and x is equal to 1, this line, okay, y x cubed, and that's my function right here. So the yellow parts are the areas that I have to find. Well, if you can see this area, which it's below the x-axis and it's negative, and this area it's above the x-axis and it's positive, and when we add those areas we'll get 0. but area cannot be 0 here. It's bigger than 0. So to calculate this, we have to find the area below the x-axis and take modulus, the absolute value of it, and then we have to add it with the positive area, which is above the x-axis. So my area will be modulus of a negative area plus our positive area. Okay, my antiderivative will be x to the power of 4 divided by 4 from minus 1 to 0, and my positive 1 will be the same. The antiderivative is the same, but from 0 to 1, as you can see, from 0 till 1. Okay, 0, 1, here it's minus 1. So, and when we insert 0, we get this, and when we insert minus 1, we get this, plus the same calculations for the rest, and when we insert 1, we get this expression, and then we insert 0, and we get 0. So when we calculate this, we get 1 over 4 plus 1 over 4, that gives me 1.5, 1 divided by 2, that's 0.5. Okay, let's go to next example. Here, find the total area of the regions contained by f of x, x cubed plus x squared minus 2x, and the x-axis. Here, as you can see, this area is positive, and the one which is below the x-axis is negative. So for the negative part, we have to use modulus. So the area will be area of the negative and area positive one. Negative one will be in modulus. So this one from from minus 2 to 0, minus 2, that's my point here, till 0. So we are calculating the positive one by this integration, and we have to add a modulus of the second integration, which is from 0 to 1. We integrate and find the negative area, and x to the power of 4 divided by 4 plus x cubed divided by 3 minus x squared from minus 2 to 0. This is my antiderivative, and second antiderivative will be like this, from 0 to 1. Okay, and we insert 0, and we get 0, and we insert minus 2, we get this expression, plus we insert 1, and we get this expression, and we insert 0, and we get 0. So when we calculate all these, we get 37 divided by 12, and that's my answer. The shaded area, okay, in the example 8, under the curve y is equal to x squared plus 2 between minus k and plus k. So this is a different example. We are not given the boundaries. We have to find them. The area here, the shaded area, is 6k. My boundaries are minus k and k. My function is x squared plus 2, this green graph. And what we need to do is that we need to find the exact here. It shouldn't be an estimation, it should be an exact value of k. Okay. In order to find k, we need to use the area that we are given. So this area, shaded area, is 6k, and that should be an integration of this function from minus k to k. So area will be from minus k to plus k, my function right here, and my area is 6k as it's given. So I write 6k and I integrate this. So my antiderivative of x squared plus 2 will be x cubed divided by 3 plus 2x. So the boundaries will be from minus k to plus k, okay, plus k. And when we integrate these, when we integrate this, we put the boundaries. First of all, we put plus k, and we get this expression, and then we put minus k and get this expression. So that will be 6k equal to 2k cubed divided by 3 plus 4k. K cubed means we should have 3 different solutions, or maybe same, but 3 roots. So one of the roots, when we find the roots, will be 0, and the others will be square root of 3 and minus square root of 3, because if our expression right here is equal to 0, then it means that one of them is 0, or either k is 0 or this expression is 0. If k is 0, that means we put here 0 and get area 0, but area cannot be 0 in this example. So that means our third root, k is 3 is equal to 0, is not correct. So we don't take that. We take k is equal to square root of 3 and minus 3. So this one will be square root of 3, this one will be minus square root of 3. So that's our answer. Now let's move on to application of integrals. Integrals are widely used and can be applied in almost every science. For instance, we use integrals to calculate the distance traveled by an object in physics. If the velocity of this object is a function of time, then a definite integral will give us the distance. This is the formula. We're integrating from t1 to t2 our function, and we get the distance, because velocity multiplied by time gives us the distance. Here's an example for application of integrals. A ball is initially at rest. It moves with the velocity of function vt is equal to t squared minus t minus 2. Find the total distance traveled in the first 2 seconds. So here it starts at t0 till t is equal to 2. My function is this one, and the area between x-axis and my function is the green shaded one. And as you know, if it is below then the x-axis, it will be negative. So I have to take the modulus. Area will be absolute value of our negative area, and that will be integration from 0 to 2, from 0 till 2. Our function t squared minus t minus 2. So antiderivative for this will be t cubed divided by 3 minus t squared divided by 2 minus 2 t from 0 to 2. Okay? And we insert 2, we get this expression, and we insert 0, we get 0. So my answer will be 10 divided by 3. Okay? That's the correct answer. Okay? Example 10. Jack's company starts to sell hamburgers. At time t0, they sell at a rate of A is equal to 1 hamburger per second. This rate increases with time by the rule AT is equal to 2t plus 1, where A is the selling rate. How many hamburgers will this company sell after their first 10 seconds of work? So solution. Area bounded by the curve of this function, A of t, rate versus time, of course, gives us the amount that has been sold. So to find the amount that has been sold, we have to take integral of our function from 0 till 10. Here is a graph of my function. The shaded area is shown you by a red color. N is the number of hamburgers, and that will be the integration from 0 till time t, my function a of t, and from 0 till 10 is from 0 till 10, my function is 2t plus 1, the antiderivative will be t squared by 2, and 2's get cancelled, and plus t, so my last expression will be t squared plus t from 0 till 10. So we insert 10, we get 10 squared plus 10. We insert 0, we get 0. And the answer will be 110 hamburgers. At the end of our lesson, let's do a reflection. Discuss these questions with your partner. What new information have you learned today? What was easy to follow and what wasn't? Would you like to know more about this topic? Ask yourself these questions. Recommendations. I would like to recommend you to read these two books and solve some examples from them. The first one is Mathematics for the International Student, Mathematics HL Core, 3rd edition, published by HIAC Mathematics. The second book is Mathematics for High Level by Oxford. References. Well, these are the references. You can go there and read more about the areas bounded by the curve and x-axis. Thank you for your attention. This is the end of our lesson.